Good afternoon. This is Math 2413. Today's November the 15th. Have a couple of announcements to make here at the beginning of our lecture. First of all, I wanted to remind you that homework 5 is due next Tuesday, 11/21, November 21st. Homework 6 is due about 10 or 11 days later on December the 1st. So please get started on those homework assignments. Don't get behind. See if you can get those finished up. This is our schedule for the rest of the semester, pretty much. Today, we're going to look at integration by substitution. We'll do a little bit of reviewing of an application at the beginning of class today, and then we'll go on and look at integration using substitution. One thing I want to point out is that this week, Exam 3 review will be posted by Friday. I've started working on the Exam 3 review, and so hopefully I'll get it up by tomorrow, but at the very latest by Friday. So be looking for the Exam 3 review. Also, I want to point out that there will be a take-home problem on Exam 3. I'm not ready to give you that take-home problem yet, but I'll give it to you as we head in towards the exam window, the testing window, and so be looking for a take-home problem. And when we talk about the exam review later, I'll mention what kind of problem we're looking at as far as the take-home problem that you're going to have. All right, and then next Monday, we'll look at integration with exponential and logarithm functions. Next Wednesday, no lecture at all because that is the Thanksgiving weekend start. The Lone Star College system campuses are all closed on Wednesday, so no lecture next Wednesday. The following Monday, we'll look at integration and inverse trig functions. So we're continuing to look at integration with different types of functions. Next, and then that Wednesday, there won't be any lecture. I will be on campus during that time period. And so if you're looking for help and you want to come on campus, you'll be able to do that on November the 29th. Monday, December the 4th, once again, no lecture. We're in the middle of the Exam 3 testing window, and so no lecture there. And then finally, on December the 6th, on Wednesday, we finish the course. And I will post a video that day to kind of wrap things up. It won't be a full-blown lecture, but we'll go over and kind of tie up some loose ends there. Finally, the final exam window opens on the 7th of December. So be looking forward to that. And as we proceed in through these last couple of days, we'll be talking about what you should start reviewing if you want to start preparing for the final exam also, because the final exam comes pretty quickly after Exam 3. Okay, so today, with all that in mind then, today we want to start off by reviewing an application of integration. So review of an application for integration. This is an example of something that's called the net change theorem. We didn't really identify that net change theorem specifically last time in lecture, and I'm not really going to do that. But what we're looking at with velocity is certainly a direct result of the net change theorem. And so if we are given a velocity function, so given v of t equals, and I'm just going to start off with a function like this, 5t minus 7. We're going to look at fairly simple functions, so don't worry about us having anything complicated here. I just want you to get the idea of how to work this. You will have a problem like this on your exam, very similar to what we're doing here. This is very similar to a problem we did at the end of lecture on Monday. Okay, so let's say this is our velocity function. Let's say the t is bounded by the time 0 and 3. So this velocity function is accurate for those time periods. So the question we want to answer here is, what is the total distance traveled in the time period from t equals 0 to t equals 3. Okay, so that's what we're interested in looking at. What is that distance to travel in those first 3 seconds? All right, so if you look at a graph for the velocity function, and so let's see. So here's my axis. This, remember, would be our velocity axis here. This is our time axis here. Time axis is the horizontal axis. 5t minus 7 has an intercept at 7/5, right? So that's 1 2/5. So let's see. Let's change our scale. So here's t equals 3. This is the time period we're talking about. And let's say that our scale on the vertical axis goes by, let's say, goes by 5. So -5, -10, -15, like that, and then 5, 10, 15, like that. All right, so at time 0, we know that the velocity graph is at -7, like that. And then it has an intercept. Remember, we said it's 7/5 or 1 2/5, so not quite at 1.5. And then at 3, this is at 8, like so. And so this is the graph of the velocity function right here. Right, that's the graph of our velocity function v. So now, what do we see here? We see that the velocity is negative. Velocity is negative from 0 to 7/5, like so. And so that means that the object, you remember, we're talking about motion horizontally, right? This is all horizontal motion that we're talking about in these problems. So in this case, the motion is to the left because the velocity is going to be negative in that time period. And then when the velocity is positive from 7/5 to 3, right now the motion is to the right. All right, so so keep that in mind, that when you're looking at a function like this, if you've got a graph of the velocity function, this graph is telling you when the object is moving left and when it's moving right. So since the velocity is negative there, the object's moving to the left. And because the velocity is positive in this interval, the object is moving to the right. Okay? Now, if you recall, what we just talked about last time was that if you looked at the integral from 0 to 3 of our velocity function, that this did not give you the total distance that the object moved, but rather this gave you the displacement of the object. All right, this is total displacement right here, and that may not be, and in this problem it's not, is not total distance. That's because this object's moving in 2 different directions, and because it's moving in 2 different directions, then total displacement is not the same thing as total distance traveled, right? If it was always moving in the same direction, then those would be the same. Total displacement, total distance traveled would be equal to each other. But because this object changes direction, that's not true. All right, so if we look at this integral, you get 5/2 t squared minus 7t. We're evaluating that using the fundamental theorem of calculus, right? And so we're going to evaluate it from 0 to 7. And so we get 5/2 times 9 minus 7 times 3. And then that would just be minus 0, that the lower limit is 0. So you get 45/2 minus 21. So that's 45/2 minus 42/2, or 3/2. So now remember that 3/2 is the total displacement. And let's say this is in, let's say the t is in seconds. here, I didn't say that at the beginning, but let's say that distance is in meters, right? And so velocity would be in meters per second. So that 3/2 of a meter is the total displacement. That means that is how much the object's position has changed in the from time 0 to time 3. So it ends at 3/2 of a meter to the right of where it started. So down here, if this is t equals 0, if this is the object's location at t equals 0, then what are we seeing here is that the object first moves to the left. When it moves to the left, we haven't talked about the distance yet, but it moves to the left from t equals 0 to 7/5 of a second, like that. And then what happens, then it changes direction and it moves to the right, like that, and that would be in the interval from 7/5 to 3. And what else do we know? We know that the total displacement of the object, that total displacement would be this distance right here, that this distance is 3/2. That's the change in the object's position in those first 3 seconds. It started off right here, right at t equals 0. It finishes right here at t equals 3. And remember, I'm drawing these lines, these rays separately so you can see the motion left and right. But remember, this is all horizontal motion. So what's the total distance that this object has traveled? Well, what we could do, there's several ways you could look at this, certainly. But if you looked at the integral from 0 to 7/5, like this, then that would give us the displacement in the first 7/5 of a second. And since the object's always moving to the left, this would actually give us the distance that the object's traveled. Now, it would give it as a negative number, but it would give us the distance traveled. The distance traveled would actually be the absolute value of this quantity. So this is the exact same interval we just talked about. So obviously the same antiderivative, but now we're evaluating from 0 to 7/5. And we know, because the object's always moving to the left in that time period, that we better get a negative number here for this answer. So you have 5/2 times 7/5 squared minus 7 times 7/5. The lower limit would be 0. And so you would have, let's see, 5/2 times 49 over 25 right there. Minus, and then this would be 49 over 5, like that. So let's see, we have the 5 and the 25 cancel there. And so that would be 49 over 10 minus 49 over 5. And so that would be 49 over 10 minus 98 over 10, or negative 49 over 10. So the negative 49 tenths tells us that that's what the object has done in the first 7/5 of a second, that it's gone 49 tenths of a unit to the left. And so here's our 49 tenths. So the object has moved 49 tenths of a unit this direction to the left. And then you can see what the other direction's got to be. You could use another integral here, but notice, because of the picture I've got drawn there, that notice this distance here simply has to be 49 tenths plus 3/2. And if you add those together, you're going to get that total distance. So that'd be 49 tenths plus 15 tenths, or 64 tenths. And that distance, that 64 tenths, is going to represent the total distance that this object has traveled right there. It goes 49 tenths. Oh, I'm sorry, that's not the total distance it's traveled. That's the distance that it traveled to the right. So it traveled to the right 64 tenths of a unit. So then what would be the total distance? The total distance put that right above here, would be my 49 tenths plus, and that's the 49 tenths of a unit that of a meter that the object moved to the left, plus the 64 tenths that the object has moved to the right, or a total distance of 113 tenths of a meter. And that's the total distance that the object has moved right there. Okay, so that's what we're after there, and you could write it as 11.3 if you wanted to. There's our total distance traveled. We only really needed one integral. If you draw a picture like I did at the very bottom, you can kind of piece together these various parts of the total trip, and then that would allow you to, as long as you get enough information, you can piece it all together, get the total distance that's traveled. Okay, so there's our answer. So we have finished that problem. And so now we're ready to go on and talk about the main topic for the day, and that is integration by substitution. All right, so now with integration by substitution, what we're going to do is expand the types of functions in which we can find an antiderivative. Because right now we're kind of limited in what we can find antiderivatives for. Okay, so this is what I'm talking about. So like, for example, remember we have this power rule, and the power rule, we know that the way we stated it was that if you had the integral of x to the n dx, that the antiderivative would be 1 over n plus 1 times x to the n plus 1, plus an arbitrary constant, and that power rule did not work if the power was -1. Right? So that was our power rule for antiderivatives. All right, well, so that allows us, with no problem, to find an antiderivative for a function like this one. If you just had x to the 10th dx, that's an easy antiderivative. Right? That would simply be 1 over 11 x to the 11th, plus an arbitrary constant. Not a big deal at all. Also, we have rules about, not just power rules, but we have rules about sums and differences, right? So that if you have a sum or a difference of two functions and you're finding an antiderivative, right, you can simply find the antiderivative of each individual function and then add those together to get the antiderivative you're interested in finding. So, as an example, if we just had this antiderivative, or this function, this indefinite integral, x squared plus 1 dx, once again an easy antiderivative. It's a power rule for the first term. We have a constant in the second term, and we know that the antiderivative for a constant is just x, or that constant times x. You could look at that as the power rule if you wanted to. And so this would give us 1/3 x cubed plus x, like this, right? And then plus an arbitrary constant. So you can do things like this. But what happens when we have a function that's just a little bit more complicated? So like, for example, I've got x to the 10th, I've got x squared plus 1 there. What if we had x squared plus 1 to the 10th, and it was a multiplication problem like this, times 2x? Now that's a harder integral. It doesn't seem to fit either of the two things that we just talked about. It's not an x to a power. It's also not even remotely practical that I could take x squared plus 1 and raise it to the 10th power and then multiply through by 2x and then find the antiderivative to that. That's not practical at all. So how do we go about dealing with an antiderivative like this one right here? Well, first thing I want to do is I want to restate the power rule. And what I'm going to do is I'm going to rewrite the power rule like this. The power rule is this form, u to the n du, u to the n du equals 1 over n plus 1 times u to the n plus 1 plus c. Now, it seems like an extremely subtle difference here, but what I want to do is I want you to look at or think about u. Think about u being some function of x. And then du, think, is the derivative of that function. Like that. And then what we're going to do is we're going to use this definition. Now, and this is one of the things that kind of got cut out during the semester because we lost the entire first week of the semester because of the hurricane. But we're going to use this definition here that if u is some function of x, then the differential of u, du, is equal to f prime of x dx. There's a geometric reason for that definition. We just haven't had the time really to kind of draw that out during the semester. Okay, so this is an important definition, something that you definitely need to keep in mind, especially as you head into Cal 2, that if u is some function of x, then du, the differential of u, is defined to be the derivative of that function dx. All right, so with that in mind, and then thinking about the power rule a little bit differently than what we've talked about before, then what you should do is think about the u to the n du. Think about it this way, that u to the n du is a function to a power times the derivative of the function. And if you have that form, then you can use a u-substitution to evaluate the antiderivative. Okay, so now look at our problem right here. Before I flip the screen, you have the antiderivative of x squared plus 1 to the 10th. All right, so what is it? That's a function to a power. What's the function? It's x squared plus 1. So we could literally let u be equal to x squared plus 1. Then is it times the derivative of that function? Well, the derivative of x squared plus 1 is 2x, right? And by the definition I wrote down just below, we know that the differential of u is equal to the derivative of this function. So the derivative of x squared plus 1 is 2x, and it'd be the derivative of this function dx, right? And sure enough, that's exactly what I've got in my integral. And so this new way of thinking about the power rule, along with this definition for the differential, seems to be fitting things together here very nicely. And so what we can do is we can look at this problem in it like this. All right, so let's go back and rewrite the problem. This is the integral of x squared plus 1 to the 10th times 2x dx. And what we saw is that we had a function raised to a power. So what we're going to do is we're going to make a substitution. We're going to let u be x squared plus 1. That's the function raised to a power. And then it's times the derivative of that function. So du, remember the way du is defined, it's defined to be the derivative of x squared plus 1 dx. So it'd be 2x dx. So now what we do is we take these two statements right here, now substitute into our integral. Right? Now, see, look what you've got going on here. There's u right there. That's u. And then this piece right here would be du. And so when I substitute in, the integral now looks like this. Instead of x squared plus 1 to the 10th, this is u to the 10th. And then instead of 2x dx, we have du. And notice what we have here is this is simply the traditional power rule. This problem, we can write down an antiderivative for this. All right, so the process, kind of what the big picture here, what do we do? Is we started with what we might call a harder integral, all right? A harder integral. And then what do? We substituted or changed the variables. So we substituted, and what we're really doing is we're changing the variables from x to u, and we are hoping that we have an easier integral when we do this. And we do. Right? This integral right here is an easier integral. That antiderivative for this one is easy to write down since that's just a direct application of the power rule. And that would be u to the 10th. I'm sorry, whoops. U to the 11th, that's better. And then 1 over 11 in the front, and then plus an arbitrary constant. Now the problem here at the end is that the integral, or the antiderivative, has the wrong variable in it. This is a function of u, but our antiderivative at the beginning had to be a function of x, right? Because everything was a function of x there. So what do? We go back to x's. So go back, put that in quotes, to x's. So how do we do that? Well, we just go back to our substitution, right? This substitution is kind of driving everything we're doing here in the problem. And so we use u equals x squared plus 1 to go back to x's at the end of the problem. And so you have 1 over 11 times x squared plus 1 to the 11th, right? Because u and x squared plus 1 are interchangeable. They're equal to each other, plus c. And we found the antiderivative right here. Right, the antiderivative for the original function would be 1/11 times x squared plus 1 to the 11th power plus c. Now remember that you can check this. You can always check an antiderivative. And you check by differentiating. Now you're not going to always do this, but it's not a bad thing to be thinking about that what you're finding is a function whose derivative is the original function, right? So if you differentiated, if you have y equals 1 over 11 times x squared plus 1 to the 11th power plus c, then y prime, the derivative of this function, would be a chain rule problem. The 1 over 11 would just sit there out in front, and then we would use the chain rule on our function to a power. So we'd bring the power down in front, subtract 1 from the power, and then multiply by the derivative of the inside, which is 2x. And then the derivative of c is 0. So you get plus 0 right there. And what happens here, the 11s divide out. And so you get y prime is equal to x squared plus 1 to the 10th times 2x. And sure enough, that's our original function. Right? And so we have found the correct antiderivative. All right, so this is the process that we're going to use when we're looking at using a u substitution in a problem. Is the basic idea is that you're starting off with a harder integral, an integral that doesn't match up with a basic integral form like it is. And this problem is not an addition or subtraction problem. It's a multiplication problem. It's not a power rule problem. It's not u to the n du or x to the n dx like it's written, or it doesn't fit any forms like that. So you're starting with a harder integral. You're changing the variables on the harder integral. You're going from, in this case, x's to u's, and you're hoping what you end up with is an easier integral. And then you evaluate that integral, and then finally you go back to the original variable at the end. So it's kind of a 4-step process for doing this. All right, so u substitution, let's write that out, those steps out. So with a u-substitution, first of all, you're starting with an integral that does not fit a basic integral form. Right? So that's not really a step, but it is really a step, because what you're doing is you're recognizing that that's true. You're starting with a problem and saying, hey, I know that this doesn't match up with the basic integral form that I've got. And so step 2, what are you going to do? You're going to change the integral so it is with respect to u. You're going to change the variables. So you're going to change the variables in the integral. U is the most common variable to use for a substitution. You can really use any variable you wanted to, but typically we use u's. And in the most common situation, we're starting with x's and we're going to u's like this. And remember, what you're going to do in this step is you're going to use this definition here. This is very key here, is that if u is equal to some function of x, then du would be the derivative of that function dx, right? You're using that definition. So you're changing the variables in the problem. Step 3, you hope, because by the way, this doesn't always work. So it really is true that you hope the new problem that's with respect to u is easier and does match in basic integral form. All right, and then what do? You evaluate the easier problem. Or the easier integral. And then finally, step 5 is you go back to x's, right? So you go back at the end and you go back to x's. Now this is for an indefinite integral. These steps right here, we're going to change this a little bit when we look at definite integrals. We won't do that right away, but during the lecture today, we will be looking at definite integrals also. And we have to do a little bit of changing around when we're talking about the limits of integration. So here you're going back to x's, you're starting with u's, and you're going back to x's. All right. So now also let's keep in mind what our basic integral forms are that we have encountered so far this semester. All right, so the basic integral forms are that you have the power rule, u to the n du, right? That's 1 over n plus 1 times u to the n plus 1 plus a constant. All right, we have e to the u du, and we're going to talk more about these in our next lecture, but we have talked about this, is e to the u plus c. Remember that this power rule does not work when n is -1, and so when n is -1, in other words, when you have 1 over u du or du over u, that is our log rule, and that's the natural log of the absolute value of u plus c. Right, so you have the exponential rule and a log rule like that. And then you also have trig rules, right? So you have sine of u du is the opposite of the cosine of u plus c. And you have the cosine of u, its antiderivative would be sine of u plus c. We have not got a form for tangent or cotangent yet. We need to deal with that. So we have some special forms for trig integrals that maybe don't come up quite as much, but we do have some special forms, right? We have a special form for secant u, tangent u, right? We know that its antiderivative would be secant u. And we also have one for, because remember the derivative of the tangent is the square of the secant. So you have secant squared u du, and you know that that is going to be tangent u plus c. Now I'm not going to write down the inverse trig forms. We talked a little bit about those with derivatives, but we're not ready to deal with those with integrals right now. So we don't have one yet for tangent. Right, we will next week at our next lecture, but not ready to do that yet. We don't have one for secant. Right, so we will need those, and so we'll talk about those next Monday. Okay, so right now these are our basic integral forms. Right, and so the idea is to try to match up with one of those basic integral forms as we go through these problems with this substitution technique. All right, so let's go on to another problem. Let's look at some more examples. So the next example, let's say we have this antiderivative, this indefinite integral, 5x squared times the square root of x cubed plus 1 dx. All right, with that square root in there and that multiplication, this definitely does not match up with any basic integral forms. Now, certainly one thing you would want to do here is you would want to identify x cubed plus 1 to the 1/2 power instead of writing it as a radical. Since we're going to deal with powers and we have a power rule, we would want to think of this as an exponent. Now, when you see a function raised to a power like this, frequently the substitution is to let u be the function. It is not always the case, but it is frequently the case to do that. And so what we're going to do here is we're going to let u equal x cubed plus 1. Right? If you have a function raised to a power, try letting u be equal to that function. And see if that works. All right, so when I say see if it works, let's follow this through. So we use the definition for the differential of u, so that's du. And du here would be 3x squared dx. Right, the derivative of x cubed plus 1 dx. So that'd be 3x squared. Now, if you're looking up at that derivative right now, you don't see a 3x squared in there, you see a 5x squared. So what we're going to do is we're going to get a little creative with the arithmetic here. And we are going to take the 5 outside of the integral. Remember, that's legal if you have a constant, right? We have a property, right? So I'm going to say that that's legal right here. Because we have a property that says that if you have the antiderivative or the indefinite integral of a constant times a function, that you can take that constant outside of the integration. Like that, right? And so that's what we're using in this step right here. Right? We're just taking that constant and moving it outside of the integration. Now, if I'm going to make a substitution, if I want to substitute du, I need a 3x squared, not an x squared. And so what I'm going to do here, and by the way, you'll see this written out differently depending on the instructor that you have that's walking you through this. But this is the way, to be honest with you, this is the way I learned it when I took calculus. So this is the way I've always written it out, is that I'm trying to match up 3x squared right here, and I only have an x squared. So what I do is I go ahead and I multiply that x squared by 3. And say, okay, I don't have that 3 in there, so I'm going to go ahead and put that 3 in there, like so. Now, that in itself would be an illegal move, because that would change the function right there, change the integral, because I'm just multiplying by 3. But we correct that issue if we also, instead of multiplying by 3 like we did on the inside of the integral, on the outside of the integral, we divide by 3. So if you divide by 3 or put a 3 in the denominator here, I mean, what would happen here? I can take this 3 outside of the integral, and when I take this 3 outside of the integral, it would cancel with the 3 that's on the outside, and it's like I haven't done anything at all. I'm left with the 5. So multiplying by 3 and then multiplying by 1/3 outside the integral is a legal move, right? You can do that. And so if if you take an integral just in general, so let's say I have f of x dx, this is always okay to multiply that function by a constant as long as you multiply by the reciprocal of the constant on the outside, right? This is a legal move right here. And when I say legal, it's legal algebraically. And the calculus is legal, right? Because I know I can take the k that's inside the integral and put it on the outside, and it would divide out with the 1 over k that's on the outside. It is an illegal move, though. It's illegal to do this. If you have a function f of x dx, this is illegal to multiply on the inside by some function of x and multiply on the outside by the reciprocal of that function. That's illegal right there, because I do not have a property that says that I can take a function and remove it and pull it outside of the integral. So that is illegal to do that. And so whenever you see me use this trick here, it will always be multiplying by a constant. I'll never be multiplying by a function. Here I'm just multiplying by 3 on the inside of the integral. So I multiply by 1/3 on the outside of the integral. All right, so now substitute. Now we're finally ready for our substitution. So the 5/3 just comes down for the right. It's outside of the integral. And then the x cubed plus 1, I mean, really what you're doing here is you're taking the, and I could write this right in here, you're actually changing the order of the factors on the inside of the integral. And now, from a practical standpoint, I would typically never write this step out, but that's what you're doing, is you're moving that 3x squared over with the dx. And so what do you have here? There's my du sitting right there, and then x cubed plus 1 to the 1/2 is u to the 1/2. So look what we have. We have u to the 1/2 du. And that matches up with the basic integral form. That's a power rule problem. Right? And so since it matches up with the basic integral form, we can write out the antiderivative. The 5/3 just continues to come down. I'll see students play magician all the time and make that constant disappear in a problem. Don't make it disappear, right? That you got to keep on carrying that constant through the problem. So keep track of those constants there. So you have u to the 3/2 right here. Remember, you add 1 to the exponent, and then put the reciprocal in front, which is 2/3. And then don't forget the arbitrary constant. And so we end up with 10/9 when we multiply those fractions together, u to the 3/2 plus c. Now don't forget, now what you've got to do is you're taking u's and you're going back to x's, right? Don't forget, you got to go back to x. And you use the substitution to do that again. You know, that substitution allows you to go from x's to u's, and it allows you to go from u's back to x's. So our u is x cubed plus 1, so this is 10/9 times x cubed plus 1 to the 3/2 plus a constant like that. Remember, you can check it by finding the derivative of that function and showing that the derivative is the original, the function we started with when we wrote out the integral. All right, so here's our, we're not going to do that, but that's what you could do if you wanted to. So there's our antiderivative there. That's our family of antiderivatives. Okay, so now what we're going to have to do is look at a lot of different situations and how to confront them. Substitution doesn't, first of all, it doesn't always work quite this straightforward, even when we have to mess with the constants. So let's look at our next example is this integral. It's the integral from 0 to 1. So notice right away that this is a definite integral, and this is x cubed times 2x to the 4th plus 1 quantity squared dx. Now, on this problem, what you certainly could do, it would not be unreasonable, is you could square out the 2x to the 4th plus 1, and then multiply through by x cubed, and then write the antiderivative that way. Because the arithmetic or the algebra wouldn't be that bad. It'd be a little messy, but not that bad. But we're going to go ahead and practice the substitution technique, and we're also going to look at the limits of integration and how we deal with those when we make our substitution. All right, so we see a function raised to a power. This is the function 2x to the fourth plus 1. So my substitution here is going to be to let u be equal to 2x to the fourth plus 1. Let u be the function that's being raised to the power. Don't use the power in there, just the function itself. And then du would be the derivative of 2x to the fourth plus 1, which would be 8x cubed dx. All right, so you can see what's going on here. I do have the x cubed in there. I just don't have an 8x cubed. And so we can use that trick that I just talked about for rewriting this integral so that we can make the substitution. So this is the integral from 0 to 1. I have 2x to the fourth plus 1 quantity squared. And then I have that x cubed in there, but I am going to multiply that by 8. Right? So this would be 8x cubed dx right there. So I'm multiplying on the inside of the integral by 8. And remember, this is a legal move as long as you also multiply outside of the integral by 1/8. Multiply by the reciprocal. That way, when you pull that 8 out of the integral, they would divide out. And it's like you're not really doing anything at all. All right, so now we're ready to make the substitution. So now substitute, and this is where the limits of integration come into play for a definite integral. So now substitute. So when you substitute, you have 2x to the fourth plus 1 squared would become u squared, and then 8x cubed dx would be du. But you see, look, if you put these, I'm going to erase these, but if you put 0 and 1 there, those limits are with respect to x. And you need the limits to be with respect to u. These limits are x values in our original integral. So those limits are x values. What do we need? We need the limits to be u values. Remember, I've got an equal sign here, and these integrals are no longer equal if I leave those limits of integration alone. Right? I've got to change those so that they're with respect to u. So notice I erase them, and how am I going to get u values there? Well, remember what you've got the substitution. You know that u is equal to 2x to the fourth plus 1. So on the lower limit for our integral, x is 0, and so you just put 0 in there for x. And so you get u is 2 times 0 to the fourth plus 1. U is equal to 1. The upper limit, that's where x is equal to 1. And so what do? You let x be 1, and you get 2 times 1 to the fourth plus 1. So u would be equal to 3. So our new limits go from 1 to 3. So the new limits here, you're going to have an integral like this. The lower limit is going to be 1. The upper limit is going to be 3. And so that's what you do right here is you change these limits of integration. All right, so that's what we're going to do. That's the way the textbook certainly writes it out this way, and this is the way we're going to approach this with a definite integral, is that when we make the substitution, we're also going to change those limits so that they're now with respect to the correct variable. Now, if you do this, the good thing is you don't have to go back to x's now, because now this problem's entirely in terms of u, but that equal sign that I've got here is valid, and so this means that the value of this integral is going to be equal to the value of the original integral. And so I don't need to go back to x's at all. Remember, a definite integral is equal to a constant, right? Just some constant that you got. And so, okay, so let's go ahead and see if we can, how we can do this then. So this is 1/8 times the antiderivative then would be u cubed, and then put the reciprocal in front, which is 1 over 3. And then we evaluate this from 1 to 3. And notice we don't ever have to go back to x's on this problem. So you have 1 over 24 times u cubed, that'd be 3 cubed, minus 1 cubed. I just factored out the 1 over 24 there. So I get 27 minus 1, which is 26. This is 1 over 24 times 26, or 26 over 24, or 13/12. And that would be the value of our definite integral, right? That the original definite integral is the integral from 0 to 1 of x cubed times 2x to the 4th plus 1 squared dx, and we're getting that the value of this integral is 13/12. Don't forget that because in the interval from 0 to 1, which were my limits of integration, this function, if you graph this function, it's always above the x-axis. The 13/12 can be interpreted as an area, that it's the area underneath this curve bounded by the x-axis on the bottom of it. So, all right. All right, so let's look at some more issues that come up as we talk about substitutions. All right, so our next problem. Now, we've actually kind of already answered this kind of problem, but I'm going to look at it anyway. You have the cosine of 6x dx, and we're looking at the antiderivative there. So the question is, what about that 6x, right? And it's kind of like the function that was raised to a power in the screen before. You know, in this screen, 2x to the 4th plus 1 was raised to the 2nd power. It's the thing you're taking a function that you're squaring, right? So it's the inside function of in some ways. Well, the inside function in this problem would be 6x. And so you're letting u be that inside function here. So I let u equal 6x. Then remember that du would be defined to be the derivative of 6x, which would just be 6 dx. And so if I'm going to make this substitution right here, what do I need to do? I need to, if I'm going to replace dx with something, well, I've got 6 dx right here. So you have cosine of 6x, and then you're going to multiply on the inside of this integral by 6, like this, and there's my 6 dx, and then I'm going to put a 1/6 on the outside of the integral, like this. I put the reciprocal of that constant on the outside. What does that mean? That means I can take that 6 outside of the integral, and those would cancel out. It's like I'm not doing anything at all here. Okay, and so once you've done this, we can make the substitution. We actually make the substitution now, so you get 1/6 times the integral of cosine of 6x, so that would be cosine of u, and then 6 dx would be du. And sure enough, I get a basic integral form, right? So this would be 1/6 times sine u plus an arbitrary constant c, and then u is 6x, so you get 1/6 times sine of 6x plus c. And there's my antiderivative. All right, so now you could do this exact same procedure here with instead of a specific constant like 6, just with a general constant. We kind of alluded to this a day or two ago. So let's say we have sine of bx dx, right? Well, the constant is just some b, and so this problem would go exactly the same as the one I just did, right? So what would we have? We'd let u equal to bx, then du would be b dx. And so what would I do with my integral here? I'm going to go ahead and write this whole thing down again. I'll have sine of bx. I'm going to leave a little bit of a space, put the dx there. And what am I going to do? I'm going to multiply by b on the inside of the integral and 1 over b on the outside of the integral. And so what do you get here? You get, when you make the substitution, 1 over b times the sine of bx, so that'd be the sine of u, and then b dx would be du. The antiderivative for sine of u is negative cosine. So this would be negative 1 over b cosine of u plus c. So the moral to the story here on these problems, on these kind here, for the sine and the cosine, is that if you have the antiderivative of the cosine of b times u, du, that its antiderivative would just be 1 over b sine of bu. And same thing for the cosine. Same thing really for all the trig functions. So if you have the sine of bu du, then you're going to get the reciprocal of that b in front. And this is going to be a negative. And negative 1 over b cosine of bu plus c. The idea here is that you're going to get these reciprocals of the constants sitting in front. That the antiderivatives are the same, but you're going to have those reciprocals sitting in front like that. So that's helpful to know. That way you don't really have to, kind of go out of your way to use a formal u substitution. What I would much rather you be in a position to do, especially as you go into Calculus 2, no matter who you take Calculus 2 from, it's going to be huge if you can look at a problem like this, cosine of 7x dx, and simply say, hey, the antiderivative for cosine is sine. All this is a constant multiple of x, so I'm just going to get a reciprocal in front here. That this is 1/7 sine of 7x plus c. Right? Same thing for the cosine, for the sine function. So if you have the sine, let's say, of pi x, pi is just a constant, right? So the antiderivative for sine is negative cosine. And so this is just going to be negative 1 over pi cosine of pi x plus c. Right? You're getting those reciprocals in front because these are constant factors that we're talking about here. All right. And that this would extend over to what might look like a little bit more complicated trig functions, but not really. So if we have the secant of 8x tangent of 8x dx, right? Remember, we know that the antiderivative for secant tangent is secant, right? We wrote this down. We know that this is, if we turn it around, it's a derivative form, right? We know that the derivative of secant is secant tangent, so we know that the antiderivative of secant tangent is secant. And all you have here is a constant multiple of x. So this is exactly like the sine and the cosine problems at the top. This just ends up being 1/8. You get that reciprocal of, and the antiderivative is secant, so 1/8 secant of 8x plus a constant, right? For a problem like this, there's not really a reason why you should have to go through a substitution every time. All right, so now let's look at some trig functions that might be a little bit more complicated. So let's look at this antiderivative, this indefinite integral. Let's say we have x secant of 6x squared plus 1 tangent of 6x squared plus 1 dx. So we have that secant tangent in there. And so that should be giving you the idea that, hey, its antiderivative is going to be a secant. But this is a problem where you really would need to make a substitution probably to get things to match up like you wanted them to. Let's see. So if you've got u is 6x squared plus 1, that's the inside function there. Right? Always let you, or at least always start with letting u be the inside function and see if that works. So if u is equal to 6x squared plus 1, then du would be 12x dx. Then remember, that would be the derivative of 6x squared plus 1, which is 12x dx by definition. So what do I need there? I've got an x dx in my problem, right? Because I have that x as a factor at the very beginning, and then I have dx at the end there. So, if you think about the way this is going to be written, if you really want to, you could change the order of the factors and put that x at the end, dx. what do you just have to remember to do here? You have to remember to multiply by 12 if you want to make the substitution, right? Because du is equal to 12x dx. So that's a 12 right there. And then what do I do in the front? I put a 1/12 here. All right, so now we formally make the substitution. And so this would be 1/12 times the secant of 6x squared plus 1, which would be u, tangent of 6x squared plus 1, which would be u, and then the 12x dx is represented by du. So sure enough, this is a function that we know the antiderivative. This matches a basic integral form. And so this is 1/12 secant of u plus a constant, and then substitute in for that u, right? Go back to x's at the end, which would be 6x squared plus 1. So this is 1/12 times secant of 6x squared plus 1 plus c. And there's our antiderivative. All right, so that's a little bit different take on a trig function. It wasn't just simply a constant factor there. So the next problem is, again, going to be still a different take on the way we sometimes will see trig functions and integrals, but where we can get by with a u substitution. So let's look at this integral, the sine to the fourth of x cosine of x dx. All right, so you really do have a function raised to a power in this one. Right, that's the sine function. And so, think about this, by the way, the sine to the fourth is really sine x raised to the fourth, like that. I think sometimes students tend to forget that that's really what you're writing when you write sine to the fourth. And sometimes it's not a bad idea to go ahead and write out sine to the fourth x as sine x, all raised to the fourth power, like that. All right, so you do have a function raised to a power. So if we were going to try to use the substitution here, because this function does not match up like it is a basic integral form. So if we're going to try to match it up as a basic integral form, we would let u be equal to the inside function. In this case, that'd be sine x. And notice this works out really well because du would be cosine x dx, which is what I have up in my integral up there. So this problem is actually ready to go as far as making a substitution. You have u, the sine x to the fourth power would be u to the fourth power, and then cosine x dx would be du. So you have u to the fourth du, and boom, that's a simple power rule problem. All right, so that works out really, really well. All right, so the antiderivative here would be u to the fifth, and we have a 1/5 in front, so that'd be plus c. And then we would go ahead and go back to x's, right? Always go back to x's at the end, remember, for an indefinite integral. So we've got u's here. We're trying to go back to x. We use our substitution to do that. And so this is 1/5 times sine x raised to the fifth power plus c. And obviously the abbreviation there would be sine to the fifth x, like that, plus c. Either way you want to write it is absolutely fine. All right, so let's look at a couple of problems. I want to kind of do this next group of problems side by side here. And there's actually 3 of them that I want to look at. All right, so these 3 problems are like this. 2x times the square root of x squared plus 1. That's x squared plus 1. Dx, and then I want to look at x times the square root of x squared plus 1 dx, and then finally just square root of x squared plus 1 dx, like that. All right, so going to kind of okay, so let's see how we can do this first problem. First of all, rewrite this as an exponent, the radical. So instead of square root of x squared plus 1, let's write x squared plus 1 to the 1/2 power. We do have a function raised to a power in there, And so this is kind of set up perfectly for a substitution. We let u be equal to the inside function like we've been talking about. And so we let u be equal to x squared plus 1. And then du, the definition, remember, is the derivative of x squared plus 1. So that'd be 2x dx. And this is set up perfectly for a substitution. We have x squared plus 1 to the 1/2 is going to be, there's our u right there, and then 2x dx is our du. And so we can make the substitution, and this works out really nicely. So we make the substitution, we change the variables. So we have x squared plus 1 to the 1/2 would become u to the 1/2. And then 2x dx would be equal to du. And boom, we've got a expression that matches a basic integral form perfectly. After a pretty quick substitution, didn't have to manipulate the integral in any way whatsoever. And then we just use the power rule there, so that would give us u to the 3/2, add 1 to the exponent, put the reciprocal in front, which is 2/3. So we end up with 2/3 u to the 3/2 plus our arbitrary constant. And then remember, we go back to x. We have u's, and now we want to go back to x's. So we use our substitution to do that. And so you get 2/3 times x squared plus 1 to the 3/2 plus our arbitrary constant. And there's our antiderivative. Works out pretty quickly, pretty smoothly, like some of the problems we were doing. Now the second one is almost exactly the same problem as the first one. Again, you're going to rewrite x squared plus 1. The square root of x squared plus 1 is x squared plus 1 to the 1/2. You're going to make the same substitution. We're going to let u be equal to x squared plus 1, and du would be 2x dx. The only thing that I have to do differently here is I don't have 2x dx in my integral. I just have x dx. So I'm going to have to manipulate this integral just a little bit. But this problem works out very similar. What am I going to have to do? I'm going to have to multiply on the inside of the integral by 2 to match up with that 2x dx. And then as long as I put the reciprocal on the outside, then it's going to work out, should work out really well. Right? That's certainly going to be the same integral. And so now I make my substitution. The 1/2 just comes down for the ride. And then I have x squared plus 1 to the 1/2, which is u to the 1/2. And then my 2x dx is going to be du. And now I have exactly the same integral that I got a second ago. Right, so I'm just going to put dot, dot, dot here. The 1/2 comes along for the ride there, and then that integral of u to the 1/2 du is going to be 2/3 u to the 3/2 plus a constant. And then the 2's will divide out right here. And then I'll have 1/3 times u to the 3/2 plus our constant. And then make my substitution. Back to go to x's, and so you have 1/3 times x squared plus 1 to the 3/2 plus c. So the problem is almost exactly the same, except instead of a 2/3 in front, you get a 1/3 in front. I had to manipulate the integral a little bit. But basically the same problem for the most part. This last problem is really different. I can certainly take the x squared plus 1, and I can rewrite that as x squared plus 1 to the 1/2. And I have a function raised to a power, so I might make the substitution and let u be equal to x squared plus 1. So du would be 2x dx. And see, that is the issue on that last integral, is that when I try to make my substitution, I have no place to put the du, right? Du is equal to 2x dx, but I don't have a 2x dx in the integral, and there's no x in there anywhere. I can't insert a 2x and then put a 1 over 2x on the outside. Remember, that's illegal to do that, right? We talked about that earlier. So it's illegal to put a 2x on the inside and put a 1 over 2x on the outside like that. And so that's not allowed. And so this is not a problem, even though it's very similar integral to the first two. This is a problem that doesn't match the forms that we've talked about in the first two problems on this screen. And so at this point, we can't do this problem. This is a Cal 2 problem, right? This is something, believe it or not, that ends up involving trig functions, and this is something that we can't do right now. So, don't get the impression as we go through this that substitution is always going to work on a problem that's not a basic integral form, because that's certainly absolutely not true. And this is a good example of a simple integral, the square root of x squared plus 1, that finding its antiderivative is harder than a simple u substitution. All right, so I wanted to kind of put these three problems together and show you these three side by side. All right, so let's now go on to another problem where the substitution maybe is not quite as straightforward, where a substitution does work, but not quite as straightforward as what we've been talking about. So on this problem, we have the indefinite integral for x times the square root of 3 plus x dx. So I rewrite the 3 plus x, the square root of 3 plus x is 3 plus x to the 1/2. Okay, so I can use exponent rules and the power rule. That makes sense to do. I have the inside function being 3 plus x, so I could let u be 3 plus x. That seems to be okay. And then du is equal to dx. All right, so in this case, notice that there is a problem, and that is that I have dx. Well, that's going to be du. That's not a big deal. And I have 3 plus x to the 1/2. That piece right there is going to be u to the 1/2. So I've got that in terms of u. The problem is I don't have x in terms of u. Right? Put question marks there because I do not have x itself in terms of u. And so what do I do next? Well, in this problem, sometimes what can happen is in your substitution, you can manipulate the substitution and solve for the variable that you still have that's not in terms of u. In this case, x is not in terms of u, so if I solve for x in this statement by just subtracting 3, sure enough, I get x is equal to u minus 3. And now I can make the substitution. Now I have everything in every piece of the integral in terms of u. Now you still have the question about whether this actually helps or not to do this. So we'll write this out. So x is going to be u minus 3. And this is a good problem to illustrate the idea that sometimes you take this substitution and you manipulate it like we did right here. The 3 plus x to the 1/2 is going to be u to the 1/2, right? And then dx is du. So sure enough, I have this integral now all in terms of u. Did this help to use this substitution? So did this help? And the answer is yes, because in the original problem, this integral right here, this cannot be multiplied. Because of that radical, and because there's terms underneath that radical, there's nothing I can do with the distributive property to multiply this out. And so I'm stuck in that original integral. But once I change over to u's, this can be multiplied, and so I still have some algebra to do on this problem. And so I can multiply this out using the distributive property, and so that's what I do. Right? I multiply that out, and I get u to the 3/2. Remember, you add exponents, minus 3u to the 1/2. Now we haven't evaluated this, or this indefinite integral. We haven't found an antiderivative, so I still have that integral symbol there. And now we can write down the antiderivative just based on the power rule. Boom, we've got it. This is going to be u to the 5/2, and then put a 2/5 in front, like so. And then on the next term, I have u to the 3/2, and I put a 2/3 in front. And I already have the 3 right there, and it doesn't matter what order you wrote those in, like that. And then plus c. The 3's divide out in the second term, and so you end up with 2/5 u to the 5/2 minus 2 u to the 3/2 plus c. And then I simply go through and I substitute in 3 plus x back for u. In other words, I go from u's back to x's here at the very end of the problem. So you end up with 2/5 times u, but u is 3 plus x to the 5/2 minus 2 times 3 plus x to the 3/2 plus a constant. And then there's my antiderivative. All right, so this problem was definitely an example of a very non-standard u substitution in that you had to manipulate the substitution itself. All right, so now we're going to go on to another problem that's similar to this one in that you have to do some work with the substitution itself. All exponents, so instead of the square root of x squared plus 1, we write x squared plus 1 to the 1/2 times x cubed dx. And like we've seen before, we're going to let u be the inside function. So we're going to let u be x squared plus 1. That would make sense to do that. So du would be 2x dx. The problem is, if I'm going to try to substitute du, I don't have 2x dx, I have x cubed dx. So what do I do here, right? That's what I got to figure out what to do. Well, let's first concentrate on getting that du in there. That du needs to be 2x dx. So I can manipulate this integral to do that. So what I do here is I write x squared plus 1 to the 1/2, and I split up the x cubed as x squared times x dx. See, now I can work on this x dx right in here. I can make that into 2x dx by just putting in a constant factor of 2 and putting in a 1/2 outside of the integral. So I multiply on the inside of the integral by 2. Right, there's my 2 right in there. And now that will, and the reason why I'm doing that is that gives me 2x dx, which is my du. And what do I have to do on the outside? I have to multiply by the reciprocal of 2, which is 1/2. Okay, so now where are we with the problem? Well, the 2x dx is du. I've got that worked in there. The x squared plus 1, right, that's a u right there. So that's going to be u to the 1/2. But I still now have this x squared sitting here that I don't have in terms of u. And this is where the substitution, again, manipulating that substitution will help. Because what can I do there? I can solve for x squared. So I subtract 1 and I get that u minus 1 is x squared. And so that's what my x squared is right here, is x squared minus 1. All right, as always then, when you think you've got the substitution set up, then the next thing is to write it all out and see if it actually helped you to do what we've just been doing. I wrote x squared minus 1 there. That's not true right there. That what's u equal to right there? That x squared is equal to u minus 1. That's better, like that. I don't think I wrote it correctly right there. All right, so let's see what we've got. We've got x squared plus 1 to the 1/2 would be u to the 1/2 times x squared, which would be u minus 1. And then times 2x dx, which is simply du. And yeah, sure enough, this actually helps. Because this, once again, is something that can be multiplied out like this. You can multiply through by u to the 1/2. And I get 1/2 times u to the 3/2 minus u to the 1/2 du. And sure enough, I can now find the antiderivative on that just by using the power rule. So the u to the 3/2, I make that u to the 5/2, right? I add 1 to the exponent. I put a 2/5 in front. Plus, and then I have u to the 1/2. I add 1 to the exponent. I have 3/2. I put 2/3 in front. And for some reason, I put a plus sign there, but that should be a minus sign, like that, and then plus c. Now be careful, that 1/2, and I have this kind of written not quite right here, that 1/2 was outside of the integral, and remember that 1/2 gets multiplied by both of these terms using the distributive property. Be really careful there. Needed to put brackets there, which I didn't have initially. So now what are you doing? You're multiplying through by 1/2. Notice the 1/2 cancels with both of those 2's, which is nice. So you have 1/5 u to the 5/2 minus 1/3 u to the 3/2 plus c, plus our arbitrary constant. And so this ends up giving us 1/5 times u, which we let be x squared plus 1, to the 5/2 minus 1/3 times x squared plus 1 to the 3/2 plus a constant, like that. And there's my antiderivative. All right, so we've kind of worked through a problem like that. So we've got some good problems here that we've worked through. This has worked out well. All right, one last thing I'd like to mention about integration. One kind of a sort of vaguely a minor topic, but I do need to mention this. It is in your textbook, and it is something we need to talk about a little bit, and that is a little bit about integration with definite integrals and even and odd functions. Now, so even functions, don't forget, first of all, our functions were f of x and f of negative x are the same thing. And in terms of a graph, it means that the graphs are symmetric with respect, or the graph is symmetric with respect to the y-axis. Graph is symmetric with respect to the y-axis. All right, so some good examples of even functions. So some examples of functions that are common, that are even functions, are the square function. And remember, any function where all the powers on x are even, there's no constants or anything like that, right? Well, you can even have a constant. I don't know why I said that, but even a constant. But if all the powers are even like that, then you have an even function. And the cosine function is an example of an even function. All right, well, what happens is this, if you're looking at integration over a symmetric interval of an even function. So what that means, kind of like this. Symmetric interval means you're integrating from negative a to a. That's a symmetric interval. And you have an even function right here, whatever that function is. Then what you can always do is, you can think about this for a second. If I have an even function, let's just use the x squared plus 2 as an example like this. If I have an even function, here's x squared plus 2, and I'm integrating in a symmetric interval. So let's go from negative 1 to 1. Well, in terms of area, notice what that represents is the area underneath the curve like this. And it is always above the x-axis, so you do get this area like this. Well, notice that that little piece right there comes in two pieces that are exactly the same size, right? So what you could really do is you could have found this integral by just integrating from 0 to 1, just this piece, and then multiplying by 2. And so that's something I wanted to point out about even functions, is that you can have the interval and go from 0 to a instead of negative a to a, and you get the same answer if you multiply by 2. Now, the reason why you might want to do this, and you'll find as calculus students that you will actually do this, is that 0 is a limit of integration now, and that's going to typically make the problem much easier to evaluate at the end. So using this idea that you can split up a symmetric interval like that for an even function is useful. Now, it doesn't work for any other kind of function but an even function. But, so as an example here, if you're going to integrate the cosine function from negative pi over 2 to pi over 2, right? If you didn't think about this, then what would you get? You'd get the sine function, and this is not a big deal either way, but the antiderivative for the sine, for the cosine is sine, and so that goes from negative pi over 2 to pi over 2, and so that'd be the sine of pi over 2 minus the sine of negative pi over 2, which would be 1 minus negative 1, or 2. But using this little theorem that I just wrote down here, what we could do is we could split up the integral. Instead of going from negative pi over 2 to pi over 2, we could go from 0 to pi over 2, as long as we multiplied by 2. And so now this is the antiderivative of of 2 sine x, or I'm sorry, the antiderivative of cosine is sine, and then the 2 trails along. And this would go from 0 to pi over 2. Upper limit, you have 2 sine of pi over 2. Lower limit, though, is 0, because the sine of 0 is 0. See, so that goes away, and what are you left with? You're left with 2 right there. Now, in this particular case, this problem, it really didn't make a whole lot of difference either way, but you will find that that can be a time saver to use that idea. All right, there's a similar situation, and this is actually simpler, it turns out, for odd functions. Now, odd functions, remember, are functions where f of negative x is the negative of f of x. They're not the equal, they're opposites. And the graphs, in this case, are symmetric with respect to the origin. Graphs are symmetric with respect to the origin. So some examples of odd functions would be our cube function, or any function. Now they have to be symmetric with respect to the origin, so you have to be careful here. Any function where all the powers are odd, and you can't have a constant in the equation at all, no constant term. So like that would be an example of an odd function, x to the 5th minus x cubed plus 2x. All the powers of x are raised to are odd. The sine function is also an example of a odd function, right? So now, if you look at an odd function, so and let me just draw one out here. Let's say we have a function that looks like this, and vaguely, let's say that this is odd. It has symmetry with respect to the origin. Doesn't exactly have that, maybe. Let me make it a little bit better than what I drew right there. I should have done a little bit better job than that, at least. All right. So let's say that this is an odd function right here. And we're integrating from negative a to a, like that. So when you integrate from negative a to a, you're talking about that region right there and this region right in here, but one of those is above the x-axis and one of them is below, but they're exactly the same size. And so what happens, the integral from negative a to a is a positive number, the integral from 0 to a is a negative number, and they cancel each other out. So like for example, the area of this region right in here was 4 in this problem. Then what would happen here? Well, you'd have the integral from negative a to a of, and let's say this is f of x. F of x would be the integral. One thing you could do is you could split it up and go from negative a to 0 of f of x dx, and then plus the integral from 0 to a of f of x dx. And what would happen? The integral from negative a to 0 would be 4, and the integral from 0 to a would be negative 4, right? Because they're exactly the same size, except one of them's above the x-axis and one of them's below the x-axis. And what do you get? You get 0. So for odd functions, this is always the case, that when you integrate from negative a to a, and you've got an odd function here, it's got to be a symmetric interval, then that interval is always 0. So an example of this would be the sine function. If you integrated the sine function, it wouldn't make any difference what the symmetric interval was, but if you went from negative pi over 2 to pi over 2, for example, you don't need to do anything there. That should be 0. All right. So those are problems those are situations that would be good to be aware of as you're going through integration, definitely. All right, so now I have some problems here that I'm going to write down on this last page, and these are problems that you can count as practice for substitution practice. I am certainly not going to pick these up, but these are problems that would be really good problems to look at to practice substitution. You have textbook homework. You have some textbook homework to turn in, not a lot, but some. But if you are looking for more problems, these problems would be good problems to look at for practice for substitution. Great practice for the test. Eventually, I'll post the solutions to these problems. And they don't fit into any general category, all of them. These are different problems, different kinds of situations that come up. Put in a definite integral in here. All right. This problem is definitely kind of a little bit different from things we've talked about, but still just a basic substitution. This problem is an example of one of those special kinds of substitutions that I looked at the very end as we were working through these problems. And my hint on this problem is to rewrite x to the fifth as x to the fourth times x. All right, and you can work that problem out. And then finally, the eighth one, 1 plus tangent of theta to the fifth power times secant squared theta d theta. These would be great practice problems for substitution. Work on these. If you have questions, I would definitely email me or attend my online office hours, and I'll be happy to help you out. But really good practice going into the exam 3. All right, you guys have a great day. Thank you very much, and have a good weekend. Please come by my office. I have office hours tonight. I have office hours Sunday night. So don't hesitate to come by for help if you have questions. I will be more than happy to help you out. Thank you, and have a great day.